Theorem 122. Vector values measurable functions. Let X, capital A, be a measurable space, and let F is equal to F1, F2, Fn from X to R power n be a function. Then F is measurable if and only if Fi from X to R is measurable for Hi. We have the following proof. For I is equal to 1 to n, defines the projection pi I from Rn to R by pi I x is equal to xi. For x is equal to x1, x2, xn in R. Since pi I is continuous, it follows from theorems 119 and 120 that if f is measurable, so is fi is equal to pi r f for I. Conversely, suppose that Fi is measurable for I is equal to 1 to n. Let Ai be less than Bi for I is equal to 1 to n, and define Qib is equal to the set of x in R power n such that AI is less than xi and xi is less than bi for all I is equal to a1 b1 times a2 b2 times an bn. Then f power minus 1 qib is equal to the intersection between the intersection of fi power minus 1 ai bi, that is in caption A. By property f in lemma 1.2, now every open subset of R power n can be expressed as a countable union of sets of the form QIB. Hence, it follows from axiom C in definition 1.1 that f minus 1 u is in capital A for every open set u in Rn, and hence f is measurable. This proves the problem. This proves the theorem 1.22. We have lemma 1.23. Let X capital A be a measurable space, and let U be from X to R be measurable functions. If phi from R squared to R is continuous, then the function h from x to r defined by hx is equal to phi ux vx from x is in x is measurable. Proof. Here, everyone can read it, please. We have following theorems. Theorem 1.24, properties of measurable functions. Let X capital A be a measurable space. We have I. If Fg from X to R are measurable functions, then so are the functions F plus G, Fg, max Fg, mean Fg, the absolute value of F. Double R. Let's Fk from X to R, K is is equal to 1, 2, 3 be a sequence of measurable functions. Then the following functions from x to r are measurable. Infimum fk, supremum fk, lim sub fk, lim in fk. Proof. Everyone can read it, please. Now we research about step functions. Definition 1.25 step function. Let x be a set of function s from x to r is called a step function or simple function if it takes or only finitely many values. Image Sx is a finite subset of R. Let S from x to R be a step function. Write Sx is equal to alpha 1, alpha 2, alpha L with alpha I is different from alpha J, for I is different from J, and define AI is equal to S parameter 1's alpha I is equal to the set of X in X such that at X is equal to alpha I for I is equal to 1 to L. Then the sets A1, A2, AL from a partition of X. That is, X is equal to union of AI, I from 1 to L. AI's intersection between AI and AJ is equal to the empty set for I is different from J. Moreover, S is equal to the sum of alpha I, he, AI, I is equal to 1 to L, where he AI is from X to R is the characteristic function of the set AI for I is equal to 1 to L. See equation 1.4. In this situation, S is measurable if and only if the set AI in X is measurable for each I. And we have the theorem 1.26 approximation. Let X capital A be a measurable space and let F from X to 0 infinity be a function. Then F is measurable if and only if there exists a sequence of measurable step functions Sn from X to 0 infinity such that and fx is equal to lim Snx n tends to infinity for all x is in x.